In this example, we are told that R134a enters a horizontal pipe operating at steady state at 40 degrees C, 300 kilopascal, and a velocity of 40 meters per second. At the exit, the temperature is 50 degrees C and the pressure is 240 kilopascal. We're told that the pipe diameter is 0.04 meter, and we're asked to A, determine the mass flow rate of the refrigerant in kilograms per second, B, determine the velocity at the exit, and C, determine the rate of heat transfer between the pipe and its surroundings in kilowatts. So what I've done over here is sort of drawn out the problem with the given information, and we're going to define what our control volume is. So our control volume is going to be inside this pipe, and we're going to have one inlet in this, and we are going to have one outlet. I'm going to call my inlet state 1 and my outlet state 2. And right here, I'm just indicating what my control volume is. So let's look at this mass flow rate. So when we're looking at A, the mass flow rate, let's start with the equation that we have for mass flow rate. My mass flow rate is going to be equal to the area times the velocity divided by my specific volume. And in this case, I'm going to say, I know the velocity at the inlet, it's V1, so all of these variables are just at state 1. So what do I actually have? Well, let's look at my area. This is a pipe, so we know my area is going to be pi d squared over 4. So pi d is 0.04 meters, and that's squared over 4 times my velocity, and my velocity is given as 40 meters per second. And we need to divide by my specific volume. Now my specific volume is going to be a property, and I am going to be looking at T1 is equal to 40 degrees C and P1 is equal to 300 kilopascal. Now we should note that 300 kilopascal is really 3 bar. And here 240 kilopascal is really 2.4 bar. And bar is good to use because that's sort of what our tables are in. So let's look this up. Let's go to a table. And for my refrigerant at 40 degrees C, my pressure is, my saturation pressure is equal to 10.164 bar. Now, we were at 3 bar, so 3 bar is less than this 10.164, so that means we know we need to use these superheated tables. Okay, so now we have to look up our pressure. Well, it turns out that 3 bar, we don't actually have it listed, but it is directly in between 2.8 and 3.2. What that means is I can interpolate or take an average of these entries, and they will give me my property. So I go to 40 degrees Celsius, and I'm looking for my specific volume. So I'm going to take this, I'm going to take this, I'm going to add them together, and I'm going to take the average. So let's look at what we get. Well, that didn't work. Okay, so my average, my V1, is going to be this 0.08089. So let's go back and figure out our mass flow rate. And so my mass flow rate is going to be 0.08089, and this is cubic meters per kilogram. Now let's check our units. So it's always good to check our units, especially on thermodynamic problems. We have a meter squared. The meter squared is going to multiply by this meter to get a meter cubed. We're going to have meters cubed over a second. Then we are going to have the meters cubes cancel out, and we're going to get a kilogram per second. So we're okay on the unit front, and this is going to be equal to, we just need to do this calculation. So we're going to have pi times 0.04 squared divided by 4 times 40, and we're going to divide this by 0.08089. So I get my mass flow rate is equal to 0.621, and this is kilograms per second. All right, so that's part A. Now for part B, we're asked to figure out what the velocity is at our exit. So we need V2. Well, we are not given, well, our area is the same. We're not given this velocity. We still need to figure out our specific volume at state 2. And we aren't given a mass flow rate. However, we can look at our mass rate balance. So this says that our change in our mass over some time is equal to the sum of our inlets, the mass flow rate of our inlet, minus the sum of the mass flow rates of our exit. We are told that we are working in steady state right here. So that means dm dt is going to be equal to 0. We have a single inlet, we have a single outlet, so that means that 0 will be equal to my inlet, the mass flow rate of my inlet, minus the mass flow rate of my outlet, and that means that this M1, which is my inlet, is going to be equal to the mass flow rate m dot 2, which is my outlet. So we just found that, and we found that this was 0.621 kilograms per second. Now this is good, because now we can still use this mass flow rate equation. But we do know that my mass flow rate is this 0.621. We know what my area is, and what we can do after we figure out what my specific volume is we can just solve for V2. So V2, this velocity 2, is going to be equal to this mass flow rate times my specific volume divided by my area. And let's figure out what my specific volume V2 is. We know that at this exit, we're now at 50 degrees C and 240 kPa, or 2.4 bar. So when we go to our table, well, 50 degrees C, it's somewhere between 12 and 14, and that's bar. So Psat is right in the middle of this, so like approximately 13.1. It doesn't matter. I can figure it out. I could take the average, but it's about 13. But we do know that my pressure that I'm looking at is 2.4. So the pressure is 2.4 bar. So this is going to be, regardless of what this actual number is, 2.4 bar is less than it. So again, we're in this superheated table. So now what we need to do is we need to go to 50, which is right here. Well, first we need to find our pressure. So my pressure right here is 2.4 bar. Then I go to 50 on this table, and I get what my specific volume is. 0.10562. So V2, put it right here, V2 is 0.10562 meters cubed per kilogram. So now let's just plug in all of these numbers. So my mass, I'll do it right here next to it. I'm afraid I'll run out of room. So my mass flow rate is 0.621 kilograms per second. My specific volume is 0.10562 meters cubed per kilogram. And now we're going to divide by the area, which is pi d 0.04 squared over 4. Now let's just put this into the calculator. And we want to divide by pi times 0.04 squared divided by 4. And we get that my V2, my velocity at the exit, is equal to 52.2 meters per second. All right, so now the last thing we need to do is we need to figure out the rate of heat transfer between the pipe and its surroundings. Now, in order to do that, we need to look at our energy rate balance. So for part C, we're going to start with an energy rate balance that says my change in energy over time is going to be equal to the rate of heat that's coming into my control volume minus the work of my control volume plus, well, we'll look at the full thing this time. So the mass of my inlet times HI plus VI squared over 2 plus GH, GZI and minus M dot E, so the mass flow rate at my exit times the enthalpy at my exit with my velocity term and my height term. Now, we said that we are operating at steady state. So this is going to go to 0. There's no work that's happening in this control volume. There's no paddle. There's no power output. So we know my work's going to go to 0. And we're dealing with a horizontal pipe, so we have no potential energy change. So my final equation is going to be 0 is equal to QCV plus MI. Well, the last thing we know is we looked at it here. My mass of my inlet is equal to the mass of my outlet. So we can just call that M dot times H1 minus H2. If I adopt my state 1's my inlet, state 2 is my outlet, then plus V1 squared minus V2 squared over 2, and that's what we have. We do need to go and we do need to figure out what H1 and H2 are. So we go back to our table and we're looking at H1 and H2. Well, for H1, we're going to have to interpolate or average these two numbers. I'll write it right here, H1 So H1 is 284.05. And H2 is going to be right here, 294.47. So let's put everything together, we're solving for Q dot. So Q dot of my control volume is equal to, well, I'm going to move this mass flow rate to the other side. And when I move it to the other side, really only my subscript's going to switch. So I'm going to have H2 minus H1 plus V1 squared, V2 squared minus V1 squared over 2. Well, we know my mass flow rate is 0.621 kilograms per second. We know that H2, we just found that. I didn't write it down, but H2 is this 294.47. So 294.47 minus 284.05. These units right here are kilojoules per kilogram. And then we have my velocity terms. So plus 52.2 squared minus 40 squared over 2. And these are in meters per second. Oops, let me get rid of this calculator. So we do know we are going to need a conversion factor when we do this operation, because we cannot add a meter per second and a kilojoule per kilogram. So the conversion factor that we need to use is we need to, let's write here, meters per second. And we need to say, all right, 1 Newton is 1 kilogram meter per second squared. So now we have some meters that are in here, and then we can say 1 kilojoule is equal to 10 to the third Newton meters. And when we do this, the Newton should cancel out with the Newton. This what do we have? What we actually have is here. So that meters per second is actually a meter squared per second squared, because each of these terms are going to be squared. So it's a meter squared per second squared. All right, so 52.2 meters per second squared. We square the unit. So when we do that, second squared, meter, so meter squared, we're left with a kilojoule per kilogram. All right, so let's do that. 52.2 squared minus 40 squared. We're going to divide this by 2 and divide this by 1,000. Then we're going to add this 294.47 minus 284.05. And we're going to multiply it by 0.621. And when we do this, we get that my Q is equal to 6.82, and we're in kilojoules per second. Well, we do have a conversion. We asked for this in kilowatts. We do know that 1 kilowatt is 1 kilojoule per second. So it's a 1-to-1 conversion, and we can get that my rate of heat transfer is going to be 6.82 kilowatts. And that is what part C is.